Chapter 14.3 Simple Linear Regression Analysis. We now know that the correlation coefficient provides us with a measurement describing the strength and direction of the linear relationship between two variables. The next procedure we'll discuss, known as simple regression analysis, enables us to describe a straight line that best fits a series of ordered pairs x1 and y. As you will see later in this section, having a straight line that describes the linear relationship between the independent x and dependent y variable provides some advantages over the correlation coefficient. We began this procedure by collecting a random sample of ordered pairs from a population of interest. The equation that describes a straight line through our sample of ordered pairs, known as a linear equation, takes the form shown in equation 14.3, where ny equals the predicted value of y given a value of x. X is the independent variable from the samples. B0 is the sample y-intercept of the straight line. B1 is the sample slope of the straight line. Figure 14.6 illustrates this concept. Figure 14.6 shows a line described by the equation y cap equal to 2 plus 0.5x. The y-intercept is the point where the line crosses the y-axis, that is, the value of y when x is 0. So in this case, B0 is equal to 2. The slope of the line B1 is the ratio of the rise of the line over the run of the line. In this case, B1 is equal to 0.5. A positive slope, like the one shown in the figure, indicates that the line is rising from the left to right. If the slope in figure 0.6 were negative, the line would move lower as it moves from left to right. If the slope equals 0, the line would be horizontal, which would mean there is no linear relationship between the independent and the dependent variables. In other words, a change in a value of x would have no discernible effect on the value of y. So far, in this section, we have focused our attention on the sample of ordered pair. However, our real interest lies in the population from which our sample was taken. The simple linear regression model for a population can be described using equation 14.4, where yi is the ith observation for the dependent variable from the population. B0 is the population y-intercept. B1 is the population slope. Xi is the ith observation for the independent variable from the population. Ei is the residual for the ith observation from the population. Our goal in this chapter is to estimate B0 and B1 based on our sample of ordered pair. The residual in equation 14.4 can be considered an error term and is discussed in more detail with equation 14.5. My students sometimes struggle with the distinction between y cap and y. Figure 14.7 shows 6 ordered pairs and a line that appear to fit the data described by the equation y cap equal to 2 plus 0.5x. Figure 14.7 shows a data point that corresponds to the ordered pair x equal 2 and y equal 4. Notice that the predicted value of y, which you can find by looking up the dotted line rising from x equal 2 and over the left is y cap equal to 3. We can verify this using the equation 14.3 as follows. Y cap is equal to 2 plus 0.5 times x equal to 2 plus 0.5 times 2 equal to 3. The value of y represents an actual data point. By contrast, the value of y cap is the predicted value of y using the linear equation. Given value of x, the difference between the actual data value and the predicted value is known as residual or EI, which is shown in equation 14.5, where EI is the residual of the ith observation in the sample. Yi is the actual value of the dependent variable for the ith data point. Yi cap equal the predicted value of the dependent variable for the ith data point. The residual for the data point that correspond to the ordered pair x equal 2 and y equal 4 is therefore as follows. EI equal to yi minus y cap I equal to 4 minus 3 equal to 1. We will revisit the importance of the residual later in this chapter. Our next step is to find the linear equation that best fits a set of ordered pair. The least square method. The least square method is a mathematical procedure used to identify the linear equation that best fits a set of ordered pair. The line that best fits the ordered pair is called regression line. The procedure can be used to find the values for B0 or the y-intercept and B1 or the slope of the line. The goal of the least square method is to minimize the total square error between the values of y and y cap, which provide us with the best fitting line through our data points. The least square method will minimize the sum of square error, or SSE, which is described in equation 14.6. Where n is equal the number of ordered pair around the line that best fits the data. Yi is the actual value of the dependent variable for the ith data point. Yi cap is the predicted value of the dependent variable for the ith data point. This concept is illustrated in figure 14.8. According to figure 14.8, the regression line that best fits the data will minimize the total square error of the 4 data points. As I mentioned earlier, the purpose of the least square method is to determine the values for B0 or the y-intercept and B1, the slope for the regression equation y cap equal B0 plus B1x. This value can be obtained in one of 3 ways. 1. Your instructor has a brain lapse and simply gives you the value. 2. You calculate the values manually using equation. 3. Excel calculates the value. Counting on the first option is an act of a pure desperation known as the Hail Mary pass of statistics, which rarely works. Calculating the slope and y-intercept manually. Equation 14.7 and 14.8 can be used to calculate the slope and the y-intercept respectively. Using the SNSCSR values with n equals 6 for our exam grade, which I asked you to put in a safe place earlier in the chapter, we first calculate the slope of the regression equation B1 using equation 14.7. In this case, B1 is equal to 4.1786. Once the slope has been determined, use it to calculate the y-intercept using equation 14.8, where B0 is equal to 70.1783. The regression equation for the exam score data is therefore as follows: y cap equal to 70.1783 plus 4.17086x. What does this regression equation mean for our grade example? Because B1 is equal to 4.1786, we can conclude that each additional hours spent studying is associated with an average increase of 4.1786 points in exam score. Also, because the slope is positive, increasing the hour of study will result in an increase in the exam score. This result is consistent with the conclusion from the correlation coefficient. The interpretation for the y-intercept requires a little more caution. Technically, the y-intercept represents the value of y cap when x equals 0. For our exam grade example, this represents the grade for a student who studied 0 hours, or y cap equal to 70.1783 plus 4.1786 times 0 equal to 70.1783. The problem with this interpretation is that we have no values for our sample where x equals 0. This makes our conclusion that a student who does not study will receive an average grade of 70 unreliable. This issue will be discussed in more detail later in the chapter. What is the predicted exam for a student who studied 3 hours? If we set x equal to 3, the regression equation, we get the following: y cap equal to 70.1783 plus 12.5358 equal to 82.7 or equal to 83. The predicted exam score for a student who studied 3 hours is an 83. We call this a point estimate for the regression equation. A little later, we will investigate the accuracy of the estimate using confidence interval. Having a straight line describe the linear relationship between the two variables has some advantages over using the correlation coefficient. First, you can observe the effect that the independent variable has on the dependent variable. For example, if a car dealership has historical data tracking the selling price of used 2007 Honda Civic with various mileage, the dealership could discover what will happen to the selling price of one of this car given an increase in each odometer reading. Second, a straight line allows you to predict a specific value for the dependent variable, given a value for independent variable. with the proper data. For instance, our dealership could predict the selling price for a 2000 Civic with 52,000 miles.